Welcome to This Explainer. Today we're diving straight into the precise and honestly almost magical mechanics of hourglass levitation nodes. We're going to look at exactly how they keep objects suspended right in midair. Imagine a massive futuristic monument, or maybe a hyper-advanced transit track, where literal tons of material are just floating, completely defying everything we know about physics, right? Well, if you've ever looked at a levitating structure and wondered about the invisible forces working overtime to stop it from crashing down, you are absolutely in the right place. We're opening up the engineering blueprints and the actual codebase to see what makes this suspension possible. Let's see the math and mechanics that turn magic into reality.
Okay, so here's our roadmap for the breakdown. First, we'll look at the hourglass levitation node itself. Second, the standard electromagnetic operations. Third, we'll explore the biocrystal alternative. And finally, simulation and execution. All right, starting off with Section 1, the hourglass levitation node, the balancing act.
So, let's start with the foundational engineering challenge at the absolute heart of these nodes. Before getting into the deep tech, we really have to understand the physical environment we're operating in. And that is this incredibly delicate pinched space known as the nanogap throat. It's the precise spatial juncture where the upper blade structure has to be perfectly suspended above the lower hourglass blade. Picture 2 points of a pyramid almost touching but never quite making contact. That empty space between them, that's the throat. And managing that empty space is literally the entire purpose of the node. Honestly, this tiny volume of absolute nothingness is exactly why engineers lose sleep at night. It's a highly unstable, volatile zone where even the slightest miscalculation means catastrophic failure.
And the constant, unyielding antagonist in this whole system? Earth's gravity. Specifically, it's pulling down on that upper blade at an acceleration of exactly 9.81 meters per second squared. Now, obviously, we all know what gravity is, but in the context of levitation engineering, gravity is a relentless monster. It never takes a coffee break, it never pauses for maintenance, and it never, ever fluctuates in its burning desire to pull that upper mass down and close the throat completely. It's a stubborn 24/7 force of nature. Because of that, the node system has to constantly, endlessly generate an equal and opposite upward force. It's basically a perpetual tug of war where you only ever tie. But if you lose for even a fraction of a second, the whole thing falls apart. So, what exactly is the goal in this crazy tug of war? Well, the system has to fight gravity to maintain a targeted levitation gap of precisely 1 millimeter. In the engineering models, this is explicitly defined as a target gap of 1 times 10 to the negative third meters. 1 single millimeter. Think about the thickness of a standard credit card. That tiny sliver of air is literally the only thing standing between stable levitation and a massive mechanical collision. And when I say collision, I don't just mean a gentle clinking of metal. In a high-mass levitation node, a sudden drop means an instant transfer of kinetic energy, shattering the delicate blade tips, frying the sensor arrays, and potentially triggering a cascading failure across a much larger structural grid. The stakes for this tiny gap are astronomically high.
Moving on to Section 2, Standard Electromagnetic Operations, the baseline tech.
To actually achieve this millimeter-perfect suspension, engineers initially rely on a highly calibrated, standard hardware model. The lower hourglass blade uses a pretty brilliant two-part feedback loop. First, a high-precision laser distance sensor is positioned to constantly monitor the width of the throat. It reads that distance and instantly tells the lower electromagnet exactly how much upward magnetic force it needs to apply. If the gap shrinks below 1 millimeter, the magnet pushes harder. If it grows, it eases up. It's an endless, high-speed conversation between the sensor and the magnet. And we're not talking about a casual chat here. This sensor and magnet are communicating back and forth thousands of times per second. It's a frantic, incredibly precise dialogue that keeps that upper blade perfectly hovering right above disaster. Now, a super fascinating limitation pops up when we look at the mass. This traditional electromagnetic setup is calibrated to stably levitate an upper blade mass of exactly 0.05 kilograms. That's 50 grams. To put that into perspective, 50 grams is roughly the weight of a standard golf ball, or maybe a large egg. That might not sound like a whole lot of weight, but balancing a golf ball exactly 1 credit card thickness above a point, fighting the unyielding pull of gravity without ever letting it wobble or drop, that requires an incredibly robust and power-hungry electromagnetic force. The margin for error is effectively zero. Which brings us to Section 3, the biocrystal alternative, the next generation. So what happens when we swap out those cold mechanics for next-generation technology? When we contrast the traditional setup against the biocrystal model, the hardware stack is radically altered. We're completely leaving behind the familiar territory of copper wire coils and optical lasers and diving straight into the realm of organic crystalline structures. Engineers are experimenting with a totally different approach to generating that upward force. We're moving away from brute mechanical magnetism to something a lot more elegant, but fundamentally distinct.
The biocrystal alternative completely replaces the electromagnets and the laser distance sensor. Instead, the lower blade becomes a biocrystal array. And rather than using a laser to measure distance and a magnet to brute force a push, it relies on a molecular harmonic grid to manage the throat space. I mean, this is straight out of a sci-fi novel. It implies a system that doesn't just statically push against the upper blade, but actively resonates with it on a molecular level. Imagine tuning two tuning forks to the exact same frequency so that the sound waves push against each other. The harmonic grid hums at a precise molecular frequency to create a standing wave of force, holding that 1 millimeter gap through pure resonance rather than electromagnetism.
But when comparing the raw parameters of these two approaches, a massive trade-off reveals itself. The target gap of 1 millimeter and the gravitational constant of 9.81, those remain identical because, physics hasn't changed. But the biocrystal upgrade actually drops the mass capacity significantly. It plummets from 0.05 kilograms down to just 0.02 kilograms. That is a massive 60% reduction in carrying capacity. In traditional engineering circles, this is a total shock. Usually an upgrade means lifting more weight, not less. Cutting your payload capacity by more than half goes against almost every instinct an engineer has, which means there just has to be a profound, hidden advantage to using this biocrystal resonance that makes this dramatic sacrifice entirely worth it.
Let's wrap up with Section 4, Simulation and Execution, Testing the Nodes. To really understand how both of these highly sensitive, seemingly divergent systems are tested and verified, we have to look at their simulation engines. Both the electromagnetic and the biocrystal systems execute identical computational loops during their testing phase. They run for exactly 1,000 steps, evaluating the levitation state constantly. 1,000 individual checks to ensure the math holds up and the upper blade doesn't fall. But why do we simulate this so rigorously? Well, because building these nodes in the real world is incredibly expensive and highly dangerous. If a harmonic grid fails in a physical prototype, you don't just get a software error, you get shrapnel. Simulations are the crucial proving ground where these mathematical models have to be absolutely perfect before a single piece of hardware is ever manufactured.
The micro-suspense in these simulations is intense. A single millisecond interval means the system has a tiny, instantaneous window to react to any shift in gravity or mass. Just think about how fast a millisecond is. At 0 milliseconds, the loop starts. At 1 millisecond, it measures the gap, calculates the force needed, and applies it. Then it does it again and again. It executes this entire life cycle 1,000 times in a single second of simulation. It's a rapid-fire, high-stakes sprint. If the calculation lags for even 2 milliseconds, the upper blade gains too much downward momentum, gravity wins, and the whole system crashes. The pacing of the code itself has to be absolutely flawless. And this brilliantly illustrates the extreme precision required. As we see directly in the code base for both models, this 1 millisecond step, written as dt equals 0.001, is the universal speed limit for keeping the nanogap stable. Whether you're using a laser and a traditional magnet or a highly advanced molecular harmonic grid, the fundamental math requires the system to check and adjust itself every thousandth of a second. It is the inescapable heartbeat of levitation. Miss a single beat, delay a single calculation, and your 1 millimeter gap completely collapses. Which leaves us with a fascinating final puzzle to consider. Why would engineers willingly trade a 0.05 kilogram levitation capacity down to just 0.02 kilograms just to use a molecular harmonic grid? Is there a hidden benefit to biocrystals, like maybe unprecedented energy efficiency or the complete lack of moving parts, that makes up for this massive loss in raw lifting power? And more importantly, as these mathematical models move out of Python scripts into physical architecture, what does this actually mean for the future of advanced levitation? That's something I highly encourage you to deeply think about as you dig further into this incredible technology.